Hello and welcome back to the course. Today we're going to look at classification of differential equations. So this is section 0.3 in the book, and this is the book is available for free at that URL, or you can buy an inexpensive paperback, and that's probably the best way to support this project. All right, so let's look at classification of differential equations. So there are many types of differential equations. It's a very wide field, but most broadly, there's sort of two main types, two main ways that we divide differential equations. The first one is ordinary differential equations, and that just means that there is only one independent variable, right? There's just one thing that we're taking derivatives with respect to, right? And then there's partial differential equations, which basically you have partial derivatives. So if you have partial derivatives, it is a PD, it is a partial differential equation. Now, I always, have to wonder that whoever was coming up with this terminology sort of didn't really like differential equations very much, right? I mean, you have, either you have ordinary, this is just ordinary differential equations, or you have partial, right? Partial is not quite complete differential equations, right? So, but anyway, those are the two types. So either ODEs or PDEs, and PDEs are quite a bit harder than ODEs. All right, so some examples, just so that we see what we're talking about. So ODE, for example, exponential growth, something that we saw last time. We have y is the dependent variable, t is the independent variable, right? K is some constant here. Or very similar, Newton's law of cooling. So here, A would be some constant, it's the ambient temperature. And we have, and Y would be the temperature, and it's, so something is cooling towards, it's going towards the ambient temperature, right? So that's, so really the rate at which the temperature changes depends on the difference between the temperature of the object and the ambient temperature, right? So that's an OD. There's Y is the dependent variable, T is the independent variable again, right? So there's only one independent variable, right? So another one, mechanical vibrations. So X is maybe, it's mass on a spring, basically. And so X is the position of the mass, and T is time, again. So we have one dependent variable X, one independent variable T. M, C, and K are just some constants, and F is some function. It's the forcing term. Maybe there's some outside force pushing your mass around, right? So those are all ODEs. Now, here's some examples of PDEs. So, for example, transport equation. It's called transport equation because it moves values somewhere. So it would be like, modeling the, very simple model of a flow of a river, right? So if you have y is the dependent equation, and t and x are the independent variables. So there is a x maybe position and t maybe time. You might have this equation. So you have two independent variables, so that's why it's a PDE, right? And here you have a PDE with a second derivative, right? So again, u here is the dependent variable, x and t are the independent variables. And you have a second order derivative here, right? So there's the heat equation. It's how heat evolves in a, if you heat up or put some sort of a, maybe you don't want it sort of equally heated, but start with some distribution of heat on a metal rod, and so at each position x, there's a different temperature, and then you let time go on, what will happen to the temperature? How will the heat distribute over? Eventually, I guess you're sort of assuming that they will sort of even out over this metal rod, right? Okay, but doesn't really matter. It's just at this point it's a PDE, right? And there are partial derivatives here, right? We have two independent variables. Here's another slightly more complicated one, the wave equation in 2 dimensions, maybe waves on a lake. So x and y here are the independent variables. And t, sorry. So x, y, and t are the independent variables. Those are, so x, y maybe are the position on the lake, t is time, and u is the amplitude of the wave, right? So with something that satisfies this equation, you have second derivatives here, but they're all partial derivatives. That's why it's a PDE. All right, now there could also be more than one equation, differential equation that's modeling whatever it is that we're trying to work with, whatever real world problem we're trying to solve. So then we say it's a system of differential equations. So let's see some examples. So for example, one of the simplest systems, right? Maybe t is an independent variable. I didn't really give a name to the independent variable here. And then we have two dependent variables, x and y, right? And we have the derivative in y is x, the derivative in x is y. Derivative of x, not sorry, in x, of x. So y prime, derivative of y. So maybe dy dt is x and dx dt is y, right? If t is the independent variable. We didn't give it a name here, right? But you have to satisfy both of them. So you have to get a solution, meaning you have to find both x and y in terms of t, and they have to satisfy both of these at once, right? So that's what it means to be a system, that you have several. Now, that could be this is an ODE, there's just one independent variable, or you could have several independent variables. For example, the Maxwell's equations from physics, right? So these are some of the most basic equations in modern physics, and so that's a system of PDEs. Right here, it might not really seem like that, but this is divergence and this is curl, and those are you can write them out, but they're annoyingly long. So I didn't want to put that on this slide. And usually it's written like this, but those are written in partial derivatives in x, y, and z. Right. So x, y, and z position is those are independent variables, and you also have time, right? This also depends on time, right? So those are Maxwell's equations, right? So the highest order derivative that appears is the order of the equation, right? That's what we, that's a number that we want to assign to every, to every equation or system, right? So, for example, this exponential growth model is a first order ODE equation, right? Because first order, because there's the first derivative, is the only thing that appears. Here you have a second order, right? This could be, maybe mechanical vibration if x was time, but it's a second order ODE because there's a second derivative there, right? Second order derivative right there, and it doesn't really matter that it was a first order derivative here. It's just we look at the highest one, right? And over here you have a fourth order PD, right? Those are partial derivatives in x and t. And you have a fourth derivative over here. So it's a fourth order PD. It doesn't really matter that there's also a second order. Could be a second order, third order, whatever. As long as they're all fourth order or less, it's a fourth order PD equation. Now, most physics that you tend to, most equations that you tend to see in physics are generally first and second order. You see high order equations. For example, this one, these are vibrations in a beam. So yeah, that can come up as well. But most of the time you see sort of first and second order equations. So we'll spend the most time on those, right? And those already, those already show you all those things that can, that can go wrong with, that make differential equations difficult, right? You already see all that in second order, really. All right. So another way that we divide equations is we say if they're linear or not, right? So an equation is linear if the dependent variable or variables, if you have multiple of them, are linear or appear just linearly, right? So they, what that means is that, it's only first powers, and we never multiply them together, we never divide by them, we never compose them with, other functions like sine or exponential or square root or whatever, right? So if you have, like, let's say an ODE of order n, so the nth, the nth derivative is the highest derivative that appears, you can always put a linear equation into form like this. Basically, you only have, let's say, the nth or the nth derivative of y appears linearly, right? So it's never multiplied by some y or some first derivative in y or something like that, right? It's just multiplied by something in terms of x, right? So maybe we call that an of x and so on, right? And then maybe there's something that doesn't depend on that doesn't depend on y at all. That's also allowed, right? So all right. So for example, second order ODE, example one, right? So we have, here are the dependent variables and their derivatives, right? So second derivative of y with respect to x, first derivative of y with respect to x, and y itself, right? And they're multiplied by something in terms of x, some functions in terms of x, and there's also some function in terms of x left over, right? Now notice that the dependence on x is not linear at all, right? So it's not that it's linear in all the variables. It's only linear in the dependent variables and their derivatives, right? That's what we mean by linear, right? So this is 1 over x, that's not linear. X squared, that's not linear. Sine of x, that's not linear. E to the x, that's definitely not linear either, right? So none of those are linear in x. That's not what we mean. Just in terms of y and the derivatives of y. All right. Now here's an example of a nonlinear equation, and you can see the nonlinearity here, right? You have the derivative of y times y, right? Or y times the derivative of y. I guess I don't know why I read it from the from right to left, but we're multiplying, the dependent variable and its derivative, right? So it's not linear. Y does and its derivatives does not appear linearly here, right? Because we're multiplying them together. Or how about a simpler one? If I have this first order ODE is nonlinear because I take x squared, right? So x is the dependent variable and I'm squaring it, so it's definitely not linear. All right, and nonlinear equations, yeah, they tend to be a lot more complicated, a lot more difficult to handle. So we hope that if we're trying to solve something that we get as linear a problem as possible, right? And every once in a while, what you do is you, even if you have a nonlinear equations, you try to, well, at least approximate it maybe locally, maybe for some some amount of time, maybe for small amount of space. You try to approximate it by a linear one because we can handle linear equations much better than nonlinear equations, which are really, really crazy, and all sorts of bad things happen for nonlinear equations. All right, now a linear equation, we say it is homogeneous or homogeneous, and I can never decide which one is correct. And then at some point I read that both are correct, but then I sometimes say that, sometimes say that. So homogeneous, homogeneous, either one spelled the same. So if I just write it, and I don't have to worry about it. But it's homogeneous if all the terms depend on the dependent variable. What does that mean? That there is nothing nothing left over, right? That's what I was saying before. So otherwise we say it's non-homogeneous or inhomogeneous or non-homogeneous, or however you would pronounce that word. So examples, some homogeneous. So here, if this thing has three terms, they all depend on y. There's nothing left over. There's 0 here. So this is a homogeneous equation. Here's another one, right? All the terms depend on y, right, or its derivatives, and there's nothing left over, right? Here's sort of the general form for an ODE, for a linear nth order ODE. Basically, there's no bx, right? There's just, you have some coefficients in front of the different derivatives, right? But there's nothing that's just left over. There's no function of purely x. So here's some inhomogeneous equations. So here, I guess this is the one that we saw before, right? It has this function of x in there that doesn't depend on y at all, right? So that's the inhomogeneity, right? That's the thing that's making it not homogeneous. Here's another one. So it doesn't have to be the inhomogeneity, of course, doesn't have to be on the right-hand side. We can always just, if we have an equation, we can always move things from left to right. So over here, if you notice, t is the independent variable, and I have a function purely in terms of the independent variable, the t, right? So because of that plus t, this thing is inhomogeneous. But otherwise, it's linear. So it's linear inhomogeneous ODE. Now, a lot of times is the inhomogeneity, this thing over here, or this thing over here, is some outside input into the system. So, for example, in the Newton's law of cooling, for example, right? It's the outside ambient temperature, the temperature of the room, right? That's giving us the inhomogeneity, right? And the way that we solve inhomogeneous equations is we solve the corresponding homogeneous equation. Basically, you first drop the inhomogeneity, solve that, and then use that to solve the homogeneous equation. So that's one of the reasons why we care about this, right? Is that we're gonna solve the inhomogeneous equations first, and then use that to get the solution in the general case. All right. So another thing that another class of these linear equations is are these constant coefficient equations, and we're gonna see quite a bit of those. So it's basically when the coefficients, when those a's are constants. The b, the inhomogeneity, we don't really care about. That could still be a function of the independent variable, but the guys in front of the y and its derivatives, those guys are constant, right? So So we have these constants. B is just any function, right? So that's what we say as a constant coefficient linear ODE. It is in this case an nth order ODE. Now, finally, another word that we use that's sort of another class of equations, in some sense a simpler class of equations, is if the equation or system is autonomous. And what we mean by autonomous is that the equation, all the coefficients, this could even be for a nonlinear equation. It does not depend on the independent variable, right? I mean, we can differentiate in the independent variable, but it's not supposed to appear in the equation in any other way, right? So, for example, this is a nonlinear autonomous equation because t does not appear, except we're taking derivatives in t, but it doesn't appear in any other way, right? But this guy, we just modified it a little bit. So because here the right hand side is x times t, so it depends on t. This is not autonomous, right? It depends on the independent variable. And a lot of times this is the independent variable is time, and so this is I guess that's where the naming comes from. It's independent of time, autonomous in time, I guess. So I'm not a linguist, so I don't know how that how that developed, but that's what it means, right? Just independent of. So if it's time, independent of time, right? Okay, so here are some examples, and it's good to try to I'll show the example and I'll give you a few seconds to sort of think about what sort of equation it is before telling you what sort of equation it is. So here, for example, so we look at this equation. The dy dt is ky. So this is the exponential growth model, right? So y is the dependent variable, t is the independent variable, k is some constant. So, all right, we'll give you a little bit of time. All right, so it's first order, just first derivative over here. It's autonomous because there's no t anywhere here, except we're taking derivative, but that's fine. But no other t appears in this equation. It's linear, right? Because I have the dy dt and y appear linearly in this equation. It's homogeneous because there's no function purely of t. That would include constants, by the way. If there's a constant, it would also be inhomogeneous. But there is no constant here, right? Or no non-zero constant. Let's be more precise. It's constant coefficient because here there's only a 1, right? 1 times dy dt, right? And then there's a k, and k is a constant, so it's a constant coefficient. It's ODE because there's only one independent variable, right? And it's an equation, not a system, because there's only one equation, right? Okay, slightly more complicated. So here, a is some constant. Let's assume that a is non-zero, and k is also a constant. Give you a little bit of time to try to think of it on your own. All right, so in the first order, again, just first derivatives. It's autonomous, again, because there's no t anywhere. It's linear. Y and dy dt do appear up to linearly. That's what I want to say. It's inhomogeneous. Why is it inhomogeneous? Well, think about how you would expand this. So it would be k times a minus k times y. Now the k times y, that's fine. The dy dt, that's fine. But the k times a is a constant, right? So that is something that's not dependent on the dependent variable, right? So you can think of it as it's a constant function of just the time, right? Well, it's independent of time, but it's it's something that does not depend on y or the derivatives of y. That's what we mean here, right? So that's the inhomogeneity. It's a constant here. It's constant coefficient because well, there's a 1 here, and there's going to be minus k in front of the y, right? So those are the coefficients, and those are constants. And it's an ODE. There's only one independent variable, and it's an equation. It's only one equation. All right. So how about this guy over here? Give you a moment. And you can always pause, if you want to have more time. All right. So it's second order, because there's a second derivative here. It's linear again, because x, the second order derivative of x in t, the first order derivative of x in t, and the x itself, they all appear linearly, right? It's inhomogeneous because of this sign t, right? It's constant coefficient. So because, well, there's a 1 here, there's a 1 here, and there's a 1 here. Those are coefficients, right? And those are all constants. And again, it's an ODE equation for the same reasons as before, right? And this is mechanical vibration. So we'll see quite a bit of those. It's mass on a spring, right? And it's actually force. There's a periodic force applies to the mass given by the sign. All right. So something slightly different. All right, by the way, this is the equation for a pendulum. So theta is the angle that where that the pendulum makes. Maybe there's the independent variable would be t for time, right? Okay, so let's see what that is. So it's second order, the second derivative over here. It's autonomous because there is no. Oh, by the way, that's something that I forgot last time. This was not autonomous, right? Because of the sign of t, right? I forgot to say that. But here, this is autonomous. This guy over here is autonomous. There is no t, right? It's nonlinear, however, right? There's a sine of theta. Theta is the dependent variable, and we have a sine of theta, right? So it does not appear linearly, right? That actually makes this equation a lot harder to solve. We'll first look at this equation. We're actually going to look at a simplification of this where we're going to linearize it, basically. We're going to look at sort of, a very similar linear equation, and that's going to work as long as theta is very small. It's not going to, give you precisely what the pendulum does, but it's going to be close enough, right? As long as theta is small, and as long as you don't do it for a long enough time. So, but it's the sort of tricks that one has to do. All right, and it's again ODE, and it's an equation, right? Okay, so final example. All right, so it's first order, It's only first derivatives here. It's linear because what are the dependent variables there? U and V. And so if U and V are the dependent variables, then they all appear linearly, right? So it's a linear equation, right? It's inhomogeneous, well, because you have things that don't depend on they don't depend on the dependent variables, right? And it's not autonomous, right? Because it depends on the independent variables, and it is constant coefficient, however, because all the coefficients are essentially 1 and minus 1. So there's a, let me get rid of this highlight. So there's a 1 here, there's a 1 here, there's a 1 here, there's a minus 1 here, right? So it's constant coefficient, and it's a PDE. There are 2 independent variables, and it's a system. There's 2 dependent variables. All right. So that's I think good enough for today. So all right. So I'll see you next time.